Hello everyone. In this tutorial video I'm explaining your fourth lab cycle program, which is to add an array of 16-bit numbers and store the 32-bit result in the internal RAM of the ARM7 processor. At the end of the program execution, the result can also be viewed in register R2. Now let's look into a concept of a program implementation. Here we define an array of an n elements which is of 16-bit wide, and we will add all the elements and store the result as a 32-bit in the internal RAM. If the number of elements in an array is n, then actually we are going to perform n minus 1 addition operation in order to sum up all the elements that are present in an array. So for that we are going to make use of 3 registers. So in this program actually R1 is used as a counter to perform total number of addition, and the size will be like n minus 1. As I told you before, n is the actually the array length, and R0 which is used to hold the address of an array, and R2 is used to hold the sum after each addition is performed. Now in this program we are using an instruction called as an LDRH. So what exactly it will going to do is it will going to fetch only a 16-bit, or else it will going to fetch only the data that is half the size of the maximum width of the register. That means if the register is 32-bit, it will going to fetch only 16-bit, and it will going to store it in its lower bits. In this program we are also using an 2 assembler directive, which is called as a DCD and DCW. So what is DCD? DCD is nothing but an assembler directives which allocates one or more words of a memory. Remember, from the memory you are going to fetch it, and the size of a memory will only be like, the boundary has been set to only 4 bytes, that is a 32-bit wide. So when you are using a DCD, so when you are using a DCW, only half word will be fetched. That means 2 byte of a boundary has been set to the memory location. So in order to define an array, we are going to an array is nothing but a constant which will going to have a fixed number of elements. So that elements is a nothing but a constant, and we are going to define that array as a constant here, which will be defined using an assembler directive DCW, and we are going to use a variable in order to hold the result and to store that result inside the internal RAM. We are going to define that using a assembler directive called as a DCD, which is nothing but a data constant decimal, which is used to store the which is used to define a 32-bit numbers, where DCW will going to define a 16-bit number, DCD will going to define a 32-bit number. Now let's come back to our program. So here I already written and executed. I'm just going to execute it one more time in order to demonstrate how exactly the program will going to work. So now I'll start with the first line. So that is, in order to initialize the counter, that is as I have defined the 6 elements here, I'm just going to set the counter as a 5, that is n minus 1 time, that is array size minus 1. Now in the second instruction I'm going to use a LDR R0 comma array, which is used to here the R0 is used to hold the address of the constant array. So now only the address will be the whatever the address of an array, constant array, will be stored inside the R0. Now the R0 will going to act as a pointer to an array elements. So now in the next instruction I'm going to use an LDRH. As I told you before, only the 16-bit of the first element. So the 16-bit of the first element will be stored inside the R2 register. Let's see. I'm sorry, I was explaining the next one. So in this instruction I've just copied the R0, that is the address of an array, which is nothing but a 30. So if you go to the location 30 00000030, now you can see an array has been defined here the array which will going to make use of a internal ROM, not RAM. So the array will be used inside the, as you can see here, the array has been defined within the program code. So it will make use of a program ROM, and the array, the element that will be stored inside the program RAM itself, that has been defined in an array constant. So now the first R0 is holding a address or pointing to an address 30 in which the first element of an array has been stored. So now when I execute this instruction LDRH R0 R2 comma contents of R0, the element that is present in an array will be stored into R0. Since I am just using a H here, that means LDRH, only a 16-bit of the data, these two numbers will going to be loaded into an R2 register. Let's see now only the first element, that is first elements of an array which is of a 16-bit will be loaded into a R2 register. Now I'm just incrementing the array, the address array. So in order to point to the next data or next element of an array, so if since it is on 16-bit, I'm going to increment it twice. So that means 2 byte I'm going to increment it. That means the address is now 32-bit. Now it is pointing to a location, element, the second element of an array. So when again I'm going to use LDRH, which will going to store that 16-bit number into an R3. See now the first two elements of the array has been stored inside R2 and R3. Now I'm going to perform the addition operation between the first two consecutive elements of an array, and again the result will be stored back into the R2 itself. As you can see here, add R2 comma R3, that means these are the two source register. Now as I point to that R2, you can see the contents of the R2, which is nothing but 1111 and 2222. If I am going to perform this addition operation, the result, which is nothing but a 3333, as I am shown here, when you add the first two elements, you are going to end up with the result 3333. That will be stored inside the R2 itself. So again the destination, the destination result has been set to R2, so these two will going to get added and the result will be stored inside the R2 register. So you can see here the the result has been updated, which is 33. Now I have n minus, as I have been set a counter, this one time addition has been performed, or so I'm going to decrement the counter here by using a subtraction instruction. The yes, whatever the mnemonic yes that has been post fixed to the sub instructions, will going to update the flag registers or conditional flags inside this CPR register. As you can see the contents of a CPR register, there are different flags we have already studied in the theory, that is negative flag, zero flag, carry flag and overflow flag. As soon as I execute this instruction, these conditional flags will going to get updated. So now as you can see, the carry flag has been generated by 1. Since I'm just going to I'm not bothered about a carry flag, I'm just concentrating on the zero flag. If the result becomes 0, that means if the counter becomes 0, I'm going to exit from the loop, or else I'm just going to continue to perform the addition operation. See, in the next instruction I'm going to check whether R0, now as soon as I subtracted one time, I'll check R0 is equal to 0 or not. If it is not equal, I'm going to just loop back in order to perform the next element addition. So now I'm going to fetch the third element by incrementing the address of the array. As you can see here, initially it was pointing to an address location 32. Now if I increment it twice, it will going to point to the 34. So now this is the location 30, 31, 32, 33 and 34. Now it will going to point to the third element of an array. See, now it's pointing. Now let's get the third element into an register R3. Now you got it. So now again the addition is performed between R2 and R3, and the result of 333333 will result in 66, and again it will going to be stored in the register R2. So again I'm going to decrement the counter by one time. I have already performed 2-time operation, addition operation. Now remaining 3 times I have to do. So again I'll compare with a 0 whether it has been, the counter has been cleared or not. If it is not equal, again I'm going to get back. So again I'm going to I'm going to add or increment the address to point to the fourth element of an address. Again it has been 36, and the fourth element, which is AA, will be fetched to the R3 register. See, again the addition has been performed. See, I'll just continue. See, this is the last iteration that I'm performing the addition operation. See, now as soon as I subtract here, the counter will going to be get cleared. See, as soon as this instruction has been executed, the 0 flag has been set to 1. So now I'm going to compare it with a 0 whether R1 is equal to 0 or not. If it is true, it will just come out of the loop, or else it will just go back to the loop in order to perform the addition operation. So now, since in my condition or my scenario it is true, it will just come out of the loop. So now in order to store the result, whatever the result that has been accumulated inside the R2 register, we have to store that into an internal RAM. So now I'm going to store the address of this variable result into the R4. Now the R4 will going to be updated with this variable address. As you can see here, this is the address of the internal RAM. Now I'll show here what is exactly the difference between an internal RAM and a ROM. So this first region is nothing but a program memory. As you can see here, this is a non-volatile memory. That means a internal ROM of the ARM7, which is used to store the program code. Now the address of this RAM starts with a 000, and it will going to end with 0007 FF. Now this region has been reserved for a reserved address space, which is used for some other kind of some other purposes. Now the address starting from 400 to 40007 FF, these three regions are used as an internal RAM of the ARM7. So if I want to store the result inside this region, I have to load this address. Now as you can see in this program, the address of the result has been stored at the starting address of the internal RAM. Now as I have been already stored the address in R4, I'm just going to update the result. Now, whatever the data, whatever the sum that has been accumulated in the R2 has to be stored inside this address. Now in order to look that, I'll go to that address 400. As you can see, before storing, the contents is 00. Now I'm going to store the 32-bit result. The input for the addition was only 16-bit. Now as I've been done the addition of all the elements that has been in the array, the result will going to be like a carry will going to be generated like that. Now the result will be like 32-bit wide, and that 32-bit wide result will going to be stored in the 4 consecutive locations of the internal RAM. As you can see here, this is the result, and the result that will be stored inside the internal RAM will going to use of a little endian method. That means a lower byte will going to be stored in the first memory location. That means 97 first, then 99, and then 02, and then 00. So after this execution, you can see here the result will going to be stored inside the internal RAM. See, now it will going to make use of a little endian method in order to store this sum of all the elements in an array. That means you are going to store a 32-bit number inside the internal RAM. This is how you are going to execute this. You can try. I'll just come out of the debugger mode. And now you can try the same program in order to for a different data, like different 16-bit numbers, whatever you need, you can just give it. If I give FFFF, let's see what my result will be like. Sorry, only 16-bit data has to be given as an input, or the element inside an array should be only of 16-bit. So this is the maximum value that has been set in that can be set in a 16-bit is FFFF. I'm just making all the elements in an array as a 16-bit. Now if you want, you can add one more data. You can set it to n number of elements, no matter, it doesn't matter. See, since I'm just using a 7 elements in an array, I'm making a counter as 6, that is array size minus 1. So save it. You can run the program. So now first the address is 30, which is of array address, in which the program the data of the program will going to be stored in the internal ROM. So you can see here all the elements here are FFFF. Say I'm just using 7 elements. This is first element, second, third, fourth, fifth, sixth and seventh. I'll directly go back to the internal RAM in order to find out the result. So before the execution of the program, my memory or internal RAM consists only a 0, which means nothing has been stored inside the internal memory. Now I'm just going to run the program quickly. So 6 times the loop will going to be done in order to perform the 6 addition operation. Why? Because as I told you before, it will going to run for n minus 1 times. So now you can see the result, which is the address of this variable will be stored here, and whatever the result that has been accumulated in the R2, that means 0006 FF and F9. Since we are going to use a little endian method, F9 will be stored first, then FF, and then 06, and then 00 at finally. So you can see the result here. This is how you are going to run the program. So if you have any doubt regarding this program, feel free to contact me. Thank you. Have a good day.